by substitution. Lots to talk about, and within this lesson, some review of just antidifferentiation. We'll practice some basic ones, and then we'll advance along to ones that need substitution. And then you go, well, why would I need substitution? Well, I got to include that in the lesson too. I got to say, why would we use this? Or like, when would I use this? And then how do I do it? Well, you have some experience in substitution. Yeah, so you shouldn't be that surprised by the things I do. Indefinite integrals. This is new, this chapter. Recall that the family of antiderivatives for a function f at x is capital F at x plus c. We need this plus c in there because we won't be able to nail down the antiderivative. Once we take antiderivative, there's a whole bunch of functions that have that derivative. That is, if you look at capital F at x plus c and I took its derivative, the c would immediately become 0 and get lost in the shuffle, sort of. We're going to need more information. So if we don't have that more information, we're stuck with the c. And that's the way integrals work. Lots of times you're stuck with the c for a while. And in this case, the capital F prime is f. We use that a lot, that capital F and little f, to go, it's sort of like f, but it's the antiderivative. And when you take the derivative of capital F, you get small f. Notice we have not yet considered a convenient notation for working with antiderivatives. That's not really true. I've already snuck this notation in. You know, I didn't seem to explain it too well, but I snuck it in because I needed it. But now we'll talk a little bit more about it. Since the fundamental theorem of calculus gives us a powerful link between antiderivatives and integration, we found out that to do integrals, we didn't have to do diagrams and hope that the shapes were good. We didn't have to do Riemann's sums. We didn't have to do any of that. We could use antiderivatives to do integrals. So this integral symbol became synonymous with antiderivatives. By the end of last chapter, it was like, when I see this integral symbol, I immediately start thinking antiderivatives. And that's not really what the symbol means. The symbol means add up all the rectangles. By the end, we were like, I know how I'm going to do it. I'm going to use an antiderivative. Okay? So that symbol sort of walks the line. It might mean add up all the rectangles, but it might just mean antiderivative as well. And so we use it that way, to use for both. So, the indefinite integral. What is the difference? Last chapter, it was the definite integral, and I would give you the lower and upper limit of summation. This was like 1 to 2, a to b. You'd always have those two things. When those two things aren't there, we just mean, okay, we don't know exactly what sum we're going to do, but at least find the antiderivative. So it's really just changing it from finding the sum to just find the antiderivative. The family of all antiderivatives of a function f at x is the indefinite integral of f with respect to x. And it's denoted by just this integral symbol f at x dx. It looks almost the same, but the only difference is you don't have the two limits of summation. And when you don't have the two limits of summation, we just mean find that antiderivative. We'll maybe do some areas later. By the end of this lesson, you'll see the whole picture. I'll do ones at the end like, okay, here's one where it's antiderivative, here's one where it's sum, and you'll see the difference. If f is any function if capital F is any function such that f prime is f, then integral of f at x is capital F at x plus c. All that's saying is when you see that little integral symbol without the limits, just find the antiderivative with a plus c there, and you're done. You don't have to go through the finding the area part of it. Okay? How does that all tie together with areas? We'll get back to it. Where c is an arbitrary constant called the constant of integration, some questions we'll find the c. We found that out in last lesson. Sometimes we'll have the information to go ahead and find the c. Sometimes we won't, depending on the question. Caution. Caution. You should distinguish carefully between definite and indefinite integrals. I didn't distinguish carefully yesterday. I just sort of walked the line a little bit. But you should distinguish carefully. When you see the a to b, you're finding the area. When you don't see the a to b, you're just finding the antiderivative, and you're leaving the area on the shelf for a while you find your antiderivative. So, a definite integral is a number. It's an area. Whereas an indefinite integral is a function or a family of functions. Your answer is an equation, not a number. Last chapter, when we did definite integrals, we'd always get a number. Now we'll get a function as the answer. Here's some examples. Evaluate each of the following. A warm-up with 5 examples of finding antiderivatives, basically. but it gives me a chance to talk about antiderivatives a little more.
So since these are indefinite, are we just looking for antiderivatives?
Perfect. Perfect statement. Actually, what was that? I spoke for 12 minutes. Luke put it all in one sentence. Since these are indefinite integrals, and I know it's indefinite because I haven't been given the limits of summation. If I'd have dropped that on you last chapter, you would have looked at it and gone, Mr. Todd, you forgot something, right? For sure. But all we mean here is just find the antiderivative, and then we'll deal with the rest of it later, or we won't. So much of this part of calculus is just about finding this antiderivative. So we're going to do 5, I'll call them easy ones, and then we'll go, okay, what if they get more complicated? And you've ran into some of those in the homework, but we need a plan. Okay, antiderivative of x cubed. Here's the basic strategy. When it's powers, you increase the power by 1, and then divide by that new power. That'll get you there every time. I got to be honest, that's not really the way I think about it when I'm doing them. I just make it work. You know, and I don't think my method's better, but I want you to know if that's what you're doing, you're okay, that's fine. So 6x squared, increase the power by 1 and divide by that power, divide by that new power. I'm going to talk about why it works in just a second, okay? And then plus 1, well, constants are supposed to be easy. You shouldn't need a crazy strategy to do constants, okay? And then a plus c. And the reason we have a plus c out there is if this function was plus 10 or plus 9 or minus 5, when we found its derivative, that would just disappear, and I would get the function that's inside the integral there. Why does this dividing by that exponent work? Well, your first move, if I went to find this derivative, is to multiply by that exponent. So you're going to have divided by that exponent for those things to cancel out and end up where you started. So what you end up here is 1/4 x to the 4th plus 3x squared plus x plus c. And these are very checkable. I mean, it's so easy to check these, is you just go ahead and find the derivative and make sure you get back what you started with. Derivative of 1/4 x to the 4th is x cubed. Derivative of 3x squared is 6x, and the derivative of x is 1. So you can easily check those. Any questions about my opening example? Right. If we knew the a and b, then we'd take this whole thing and sub in the b, and then we'd subtract that whole thing, sub in with the a, and the constant would be in both terms and would cancel. And that's why we got away with ignoring it last chapter. And I just sort of glossed over that. I went, don't worry about the c's. You know, the reason we don't worry about the c's is because the c's always cancel, because it's going to be this minus that thing again, and it's going to be c minus c. So the c just goes, yeah? Good news. Good news that it all falls into place. Any other questions there? I got my PowerPoint here in front of me. I want to paste this lesson carefully. I don't know if we'll make it, but if it's two sections, that's okay. Integral, is that x to the negative 3/4?
Yeah.
All right. Now, does this method work? See, these are the ones that my method may be a little bit superior, because you're like, okay, increase the power by 1. So negative 3/4, add 1. That'll be 1/4. And divide by your new exponent. So divide by 1/4. So that'll be a 4 out there. Plus c. You hear the tentativeness in my voice? Once you have that tentativeness in your voice, you're close to being able to be very good at integrals, where you're like, I think this might be right. How do you know? You just take the derivative and check. 1/4 times 4 is 1. Okay, that's good. That worked out. And 1/4 minus 1 is negative 3/4. Yes, this is really good. This is the answer. And the plus c is out there. So some of these look really hard, and then you do them, and they're not all that hard. But maybe have both methods available. The method where you add 1 to the exponent, divide by the new exponent, and also just like, let me just get the thing that works here. You know, like, because like once you knew it was 1/4, I think it's easier just to think, oh, it's a 4 there, than it is to go divide by 1/4. You know, but practice will get you your own exact method here. Questions about this one? On to C. Integral of x squared minus sine x dx equals, okay, x squared. We're back to this strategy that actually the more I practice it, the more I'm falling in love with it. I don't have to think anymore. X squared becomes x cubed and divide by the new exponent. Why does it work? Is because immediately if I go to find this derivative, 3 times a third is 1. Reduce the power of 1. Good. And then negative sine x. Okay, then you got to be careful with the plus or minus. Me personally, I immediately, as soon as I see sine, I go, well, I know it's cos. Cos and sine go back and forth. Then I just think about the sine, S-I-G-N, the positive negative part separately. I go, okay, the derivative of cos is negative sine, so this is positive. Easy to mess you up. I think you have to check it to know. I think so that you have to go, okay, I think it's right. I think I got the right positive negative part. So derivative of cos, negative sine, oh, that's right, okay? And then plus c. The plus c will start happening automatically. You'll feel your pencil just automatically writing the plus c when you're doing integrals because it's always there until we get more information and can find out what this c is. What's the more information? Yesterday, the initial value. Some point to sub in. Last chapter, limits on the integrand. You know what I mean? Like, so if we have those things, then the c, we can take care of the c. If we don't have those things, boom, that's the answer. Plus c, don't be upset that that's where you end up with. Any questions about that one? D. Oh, this is the beginning of trouble, probably. Yeah, this is the beginning of like, well, what do I do with this? Anytime, yeah, if you're asleep, now's the time to wake up and listen.
Should we multiply?
Yeah, for sure. We're going to multiply this out and make our life easier. But anytime you see a product in the answer, then you put on the extra bank of thinking lights. You're like, hold on now. Now I got to do some thinking. That's what today's lesson is about. What do I do when there's things multiplied together? And I'm going to come up with some strategies, but this one isn't too bad because we've got our grade 10 math that can handle this situation and foil this thing out. Yeah?
One thing, I'm looking at the properties, and if we have like a constant variable for, like, could we split this into 2 integrals added where one of the brackets multiplies by the integral of the other?
Integral properties don't allow you to multiply the two of them. Allows you to add and subtract. So we can take 2 integrals that are added and subtracted together. In fact, we already did it. When we were here, we didn't even hesitate. We just said, take the integral of x squared, it's 1/3 x cubed. Take the integral of sine x, it's cos x, and we just went ahead and said, oh, we'll just break those apart. So we didn't even ask the question. When it's adding and subtracting, integrals just break apart like that. And the reason it happens is because we're just adding up a bunch of rectangles, add up all these rectangles, subtract all those rectangles. Oh, I can just do them separate because they were just adding and subtracting. In this situation, adding and subtracting is very friendly. Multiplying and dividing is not. Yeah. So here we go. Grade 10 math it is. Yeah, foil it out. 2 plus t squared. I don't know about you, but this is where I usually make my mistakes. It's not in the complicated ones I mess up. It's when I have to go back and foil. I think part of my brain shuts down. It goes, oh yeah, just some foil, no problem. And then all of a sudden I drop a negative. So I always check afterwards. 2 plus t squared minus 2t minus t cubed. Any collecting to do? No good collecting to do. It would have been nice if there was some collecting to do. But now I'm hope free once it's just a regular polynomial. 2t plus 1/3 t cubed minus t squared minus 1/4 t to the 4th plus c. I did that really fast to show that these don't have to take forever once you get good at them. Then I always check. Derivative of 2t is 2. Derivative of 1/3 t cubed is t squared. Negative 2t, negative t cubed. Yeah? But your strategy still works. Add one to the exponent and divide by the new exponent. Always works with polynomials. Is there any questions there on that one? Try to keep looking at my notes. Somewhere in this lesson, there's a special note I have to make about this, and I don't want to miss it. Yeah, I guess probably traditionally we would put it in degree order, right? That is not a rule. It's like Won't this make your life easier if you go to factor it or anything that might come next? Yeah, and so yeah, technically I should do that. Yeah. Other questions there? The last of the opening examples is integral of cos 4u du. And again, this starts to tiptoe into, so okay, this lesson's supposed to be about when the integral's two things multiplied together, what am I going to do? And the answer is, I don't know. I don't know. I don't have a rule. We're going to have to start thinking. And if there's something chain rule inside, what am I going to do? And I'm going to just gloss over this one a little bit. I'm just going to land this thing, and then we'll start talking about some more complicated examples in a minute. Equals. Go ahead.
So would that be sine for you?
Sine for you. Okay, life is good. Sine for you. And if you didn't know, I'm gonna let you back in a second here. If you didn't know for sure, you'd be like, well, I know it's at least sine for you. The derivative of sine for you is cos for you, so I'm well on my way. But what's the other piece of the puzzle?
The inside term is for you, so you need the derivative of that.
Yeah, when I go to take the derivative of this, it'd be sine for you times a 4. This doesn't have a 4, so how am I going to have something out there that deals with the 4? A quarter. That's sort of the same thing we were doing before, dividing by that exponent, but you're dividing by what's inside. And you're like, well, that's fine as long as what's inside only produces a number. If what's inside produces something other than a number, then the party is on. Okay? So I don't know if we need a special technique here, even though the technique I'm going to show you today will handle this thing if you have trouble with those coefficients. Okay? But you can take that derivative and check, and that's the kind of one that maybe even trial and error would get you there. Someone called it trial and error, who texted me and said, oh, is there something better than trial and error? And I said, sometimes, yeah. It won't work out the way you're hoping. There won't be a recipe here. That's why integrals are so hard. You have to look at it and go, okay, what do I got? Right now, you don't have enough weapons in your bag. I'm going to give you a brand new weapon coming up in a minute. Yeah. That was the opening 5 examples. Okay. So you're like, but what do I have to watch out for then? You've shown me some basic ones, but what do I have to watch out for here? And here's a list. Kira's going to love this. Here is a study page list of all the antiderivatives, not you should know, no, that I want you to know by the time I finish talking about this. We'll go through each one individually. We'll take the time to look at them and make sure that most of them we know. And then the couple that we don't, we got to talk about, okay? Oh, that's where I am. That's the important note here, coming right up. These examples coming up. Okay. So, if there's a coefficient inside an integral, you can just bring the coefficient out front. Common factoring works here. If there was a common factor on every single rectangle, I can bring it out front. We saw that when we had to type it in the calculator those times. If there's a 1/4 in every little piece, I can just bring the 1/4 out front. And this is what we were just talking about a minute ago. If you've got two integrals added together, you can do them separate and then add or subtract them after you do the integration. This is the formula for what I was talking about. If you've got something with an exponent of n, you increase the exponent by 1, but then divide by that new exponent. This is a very complicated way to say what I was saying, which is increase your exponent by 1 and then divide by whatever your new exponent is. All right, this one gets, okay, I got to take the time to make PowerPoint give me a pen here. This is the one you got to worry about. This is the one that gets, highlighting red's not going to do it. This gets the red circle because we need to talk about this one. It's easily forgotten. When you see 1 over something and it asks for the antiderivative, it's easy to forget that ln will exactly do that. Now, something new has popped up. Ln of absolute value. I'm going to deal with that in the next few minutes. Why in the world would absolute value pop out in this? And we got to talk about that in just a moment. So I'll come back to that. That gets a question mark going, you better tell me a little bit more about what's going on here. And I will in just a minute. Here's some ones that maybe are a little better. The integral of cos is sine. The integral of secant squared is tan. And the integral of secant tan is secant. This is the list of derivatives you're supposed to know, except in reverse. You're supposed to know that the derivative of sine is cos, the derivative of tan is secant squared, the derivative of secant is secant tan. So it's just all in reverse. No, when you do integral of sine, you need negative cos because the derivative of cos is negative sine, and so you get an extra negative in there. The derivative of cotan is negative cosecant squared, and derivative of cosecant is negative cosecant cotan. Here's what's coming. My gift to you. I'm going to write all these derivatives on the board on your test. Not the integrals, the derivatives. So the forward derivatives. That list of trig derivatives, I'm not going to make you memorize. We got too much going on. You'll be able to look up and see the trig derivatives, including these guys. Yeah? When we get there. Will we have all of those in time for the next test? I don't know. But we're getting there where maybe we could start to use them. Okay? So I don't want you to panic about this list. I want you to understand it. If the derivative of sine is cos, the integral of cos is sine. Yeah? Exponential. Well, e to the x, always there to bail us out and make us feel good. The integral of e to the x is e to the x. It's good news. And these last two. Oh, boy, what a mess. Integral of ln is u ln u minus u. You're like, what? That gets the big question mark. And I'm coming in just a minute. I'm going to try and explain these last couple. And this one comes out of that one. So we need these two first. And then these ones pop out of that once I have those two. If I can convince you these two don't become quite so bad, right? So, is that the list of ones that I think you should know at this point? No. It's the list of ones that many of which you should know, and a few of which we need to add to your bag of tricks, like right now. Example. Use differentiation to verify the following antiderivative formulas, and I think it's the ones that those two right there. Question for discussion. Yeah, I'm all over it. I know, question for discussion. Thank you, PowerPoint. I hope these are in my other file here, where I can do some work here. We'll keep those ink annotations for now. Switch over to here. And if it's all, there it is. There it is. Two things to discuss. Why is this the antiderivative? Why is the antiderivative of u to the negative 1, ln u? That part will be not too bad. And then why did this absolute value pop into all this? Okay, those two things. I'll start with this. Let y equal ln of absolute value of u plus c. Therefore, y prime is 1 over u. That part's not too crazy. You got to watch out for it. And when you see something just in a denominator, you're immediately thinking ln. Yeah, when you see just something sitting in the denominator. That came up in the test, right? I dropped that on the test for you. Most people got it. It was a nice little question on the test. Now, what about this absolute value? Okay, here's the deal. They gave me a function, 1 over u. Consider the graph. Y equals 1 over u. What does it look like? Or 1 over x, or 1 over whatever. What does that graph look like? Yeah, Jacob's making the little signs in his head, or the little shapes in his head. Do you remember this thing? I'm beating the 11 u's to death with this right now, or the advanced functions with that. There's 1 over u. They said, find this integral. So you answer, I know how to do it. 1 over u, the integral is, here, you go over there, ln u. Yeah, you say the integral's ln u. I know, ln u. You're not worried about the absolute value for a moment here. So you go, integral is ln u. Okay, my job in the next 2 minutes is to understand why that is an incomplete answer.
Because any x value below 0 is unreal?
Yeah, when we just have ln, we just go ahead and go, no, ln only exists over here. Sorry, no, we don't have any function over there. And that's fine when we're just dealing with ln. But this question didn't ask that. It asks, what's the antiderivative of 1 over u? Tell me what the slope is in all these spots. And this function says I don't exist at 0, but I exist in the negatives. So I need a function that exists in the negatives. But it's ln. Easy, easy solution. Here is the graph of ln. Check this out. This is great stuff. Here's the graph of ln of absolute value of x. It's so good. I don't know who came up with this, but I'm sure it was a duh moment for all the mathematicians of the time. Somebody said, oh, why don't we just use ln absolute value? And like, duh, of course. Ln absolute value looks like this and like this because it takes the number and takes the absolute value first, then ln can handle it. Let me say it another way. Ln's like, I can't help you. I can't do negatives. I can't do it. I'm out. Absolute value goes, what if I made them positive for you? Are you okay then, princess? Are you going to be okay? And ln goes, well, I guess that's okay. If you make them positive, then I'll deal with them. Yeah? And sure enough, that's exactly what happens. Ln of absolute value of x is the perfect function to find the antiderivative of 1 over x. Now you got to remember to do it. Anytime you run into 1 over something, you got to go ln of absolute value. Of course, I didn't hold you to it in the last test. I hadn't even shown it to you yet. Yeah, but we need that absolute value's got to be there. Sometimes it matters and sometimes it doesn't as it comes up. Sometimes it's going to be like, oh, well, it was going to be positive anyway. It's going to be okay. And then sometimes it really matters. Oh, do you have any questions there? The short answer, I took 12 minutes to explain it, but the short answer is, why is the absolute value there? Because 1 over x exists everywhere and ln doesn't exist everywhere. By using ln of absolute value, now ln of absolute value exists everywhere. No, not everywhere. Neither one exists at 0. They can agree on 0. They agree that 0 is out. But 1 over x wants negatives as well. Any questions there? It feels like I'm just cruising along, right? If you're watching the slides here, I'm on slide 5 of 8. You're like, are you going to get done, Mr. Ty? Are you going to be close? And the answer is no, I'm not. That last slide's a whole lesson in itself. If we get partially into the last slide, we'll have had a great day. What's next? Oh, this mess. This mess. Yeah, I do not have this mess memorized. I'll admit I don't have this mess memorized. It never came up on anything I did where you had to have this memorized. This is what it would normally say, is they'd say, prove this is true. The only time I can remember running into it. Not that your prof might not. Maybe your prof wants this memorized. I don't know. For now, let's prove it's true. That if you had to do the integral of ln u, this will work. This is the integral of ln u. And here's how I do it. Let y equal u ln u minus u plus c. It's really fun to say. Maybe it's not that bad to memorize because it's so fun to say. U ln u minus u. Apparently, this derivative will be ln u. It looks impossible, right? It looks like, how could this possibly be the deal? But check this out. Y prime equals derivative of u ln u. Okay, do we have derivatives available to us? When was the last time we did any real derivatives? Late January, yeah? Product rule. Derivative of the first times the second plus derivative of the second times the first. And I'll hesitate there to make sure you're with me. I've done the product rule on that first one. Just take a second to see, get your scraper out, scrape some rust off your derivatives, and take a look at that and see if that's derivative of the first times the second plus derivative of the second times the first. Happy? At that point, you're skeptical. You're like, I don't think this is going to come out to ln u. To which I go, maybe it will. There's ln u. Derivative of negative u, negative 1. Derivative of c, I'm going to write the plus 0 just to really keep establishing why we keep putting that c out there is because I don't really care what's out there. That could be a plus 7, a plus 9, minus 20. It's going to be 0. Still maybe feeling skeptical until I tidy this up a little bit. Y prime is ln u. 1 over u times u is 1. And it works. Yeah? So at worst, me, personally, at worst I'd say prove that the integral of ln u du is u ln u minus u plus c. I don't know that I would be cruel enough to just drop the integral of ln u on a test at this point. I don't think that's really my deal. Would the AP calculus people do it on their exam? Well, that's why we're going to get this book later. And we'll find out whether they're going to put it on their exam or not. Do you have any questions on that development? Yeah, so imagine if it's a 10, what's the derivative of 10? 0. 26, 0. Negative 14.8, 0. So that's why that c is out there, is because we don't really know that there could be something else out there. There are lots of functions who have this as their derivative. Yeah? But they all differ by a constant. They all just been moved up and down. That's all. Okay, back to here. And did I do what it asked? Did I do the question for discussion? Why do we use the absolute value here? I think I did. A simple answer is 1 over u exists everywhere. Ln u doesn't. But if I make it ln absolute value of u, now it exists everywhere and everybody's happy. Yeah? A note on Leibniz notation. A note on Leibniz notation. We know that the differential dx is the definite integral. In the definite integral, a to b f at x dx is related to the Riemann sum. This came from Riemann sums. This came from adding up a bunch of rectangles. But is it necessary in the indefinite integral of f at x dx? That is, why is this dx always hanging there? Does it matter? And the answer is yes, it really does matter. It hasn't mattered too much to us. When we saw integral of f at x, we just went ahead and went, oh yeah, find the integral. We didn't worry too much about the dx, but it matters. Are integral of f at u du and the integral of f at u dx the same thing? That is, if I'm talking about a different variable at the end, du versus dx, do I get the same thing? And the answer is not necessarily. Yeah? It really depends on what u and x are. You know, what the relationship between u and x are. If the relationship is simple, then maybe yes, they're the same, but maybe not. So here's an exploration that we got to do to find out if these things are the same. Did I put this exploration in my other file? I don't know if I did. My brain is a little fuzzy on this. So let's just take a look and see if it's the next thing I got on there. If not, you get to see me scramble. Oh yeah, I did. Look at that. All ready to go. A little small though for Mr. Todd's old eye. So here we go. All we're doing is finding out, is the integral of f at u du and the integral of f at u dx, does that mean the same thing? And my answer is, depends on the relationship between u and x. And so this, they give us a u and an x, and they say, okay, go ahead and figure out these different things. So, got to do these carefully because the wording here is weird. Find the integral of f at u du as a function of u. So I want to do integral of f at u du. So f at u is u cubed. Just put that in there. Nothing too complicated here. Finding the integral of f at u du because they gave me f at u, which is u cubed. So that's equal to 1/4 u to the power of 4 plus c. Using that trick where I went, okay, add 1 to the exponent, and then divide by my new exponent. Find integral of f at u du as a function of u. Oh, I did. I did that. I'm done, number 1. Okay. There's something about the wording here that makes me go slow. You know, I'm nervous about the wording here. So number 2. Can I fit it in here? I don't know. Number 2. Use your answer from question 1. Okay, I got my answer from question 1. 1/4 u to the 4 plus c to write integral of f at u du as a function of x. So I found out that the integral, I'm just continuing on here. Question 2 is just a continuation. So I get 1/4 u to the power of 4. Well, what was u? Oh, it's up there. Yeah? U was x squared. And that's all to the power of 4 plus c. 1/4 x to the 8 plus c. Let me just look at that and make sure I've done a good job here of writing it. 1 and 2 was just a continuation of 1. So that's why I just kept going on the equal signs. Is they said, well, don't express it in terms of u. Let's get x's into this. So I went out and I said, okay, u equals x squared. So it's 1/4 x squared to the power of 4, which is 1/4 x to the 8th plus c. If you're feeling a little confused, all I'm trying to do is find integral of f at u du, integral of f at u dx, and compare the two. That's all I'm up to here. And now I've got a nice expression for f at u du in x's. So that's like part 1. I know they divided it into 1 and 2, but that's really part 1 of this problem, of this exploration. So it says show that f at u is x to the 6th. Okay, so f at u is u cubed equals x squared cubed equals x to the 6th. Good. F at u is x to the 6th. All I did there was take the x squared that they told me u was and sub it into f at u. So it says show that f at u equals x to the 6th. Okay, now find integral of f at u dx. Okay, so integral of f at u using x this time instead of u. So it's the integral of x to the 6th dx. F at u is x to the 6th. I put it in there. And then that answer is 1/7 x to the 7th plus c. Number 4. Are the questions to 2 and 3 the same? And the answer is no. They're not the same. So they're not necessarily the same. Are f at u du and f at u dx the same? No, they don't have to be. I don't want to just say no, because this relationship worked out that they weren't the same. But we can't walk around believing that integral of f at u du is the same as f at u dx. As a side note, I'm not setting you up here. I'm not setting you up for a nasty communication question on the test on this particular topic. I just want to mention it that the du and dx matter. That's all. Just mention it for now. Any questions there? Tricky, tough example. I'm going to finish the next example and then leave substitution for tomorrow. And then I'll look up on your homework where that leaves you, because I know there was some confusion some people had about which day's homework. And then I want to talk to you about the test too. So that'll give us time at the end. So one more example, I think it was. There's a similar example. Complete on a separate page. Okay, do I have that one here? Basically the same thing again, so I'll do it fairly quickly. It's like, because that first time through, it's like, I don't know what you're up to here. It says find each of the following antiderivatives in terms of x. So A says find integral of f at x dx. F at x is x cubed plus 1. And I'm finding that with respect to x, and I get 1/4 x to the 4th plus x plus c. Was that too fast? Here, you just take a look at that and see. That part was not supposed to be difficult. Integral of f at x dx, they gave me f at x, x cubed plus 1. Find its integral, 1/4 x to the 4th plus x plus c. Good. B. Question? No? No question? That's good. Now find integral of f at u du. All right. Integral of f at u du equals integral, okay, f at u will be u cubed plus 1 du, which will be 1/4 u to the 4th plus u plus c. This is not very exciting. Why is this even here? I'm getting the same thing. So, someone read the question and tell me what I forgot in B as opposed to A. Yes, but here, find each of the following antiderivatives. I did. In terms of x. Major league detail at the end, go get your answer in terms of x. So when I do go to put the x back in, which is what you said, is that I've got u as x squared. I get x squared to the 4th plus x squared plus c. Let me just check this because I feel like I'm in my own brain. I feel like I'm rushing my own brain a little bit here. So u to the fourth is x squared, fourth is x8, and then x squared. Okay, here's a big moment. If before you came in today I said, is the integral of f at x dx the same as the integral of f at u du? It would be awfully tempting to say yes. You'd be like, what difference does the variable make? And I answer, it depends on the relationship between u and x. Yeah, that's what really matters here. Question, Luke.
Why is f of u plus 1?
What's that?
Why is f of u
Right there. F at u would be u cubed plus 1.
But that's in terms of x. It says u equals x.
Right, so if it says f at u, I'm saying take the function f and sub u into it.
Oh, okay.
Yeah, that's simple. Good. Good job being skeptical, but the skeptical part is over here. Yeah? That integral of f at u du is not the same as the integral of f at x dx, depending on what the relationship is between u and x. And it has to do with the chain rules buried underneath all this, going, you got to multiply by chain rule and all this. Yes?
So if you're putting u's in there, if u's equal to x and you're putting u into a function of x, shouldn't that be like x?
Why it bailed me out is because this one was du. They wanted f at u du. So I could just do it with u's. This question I was doing it in u's. I only went back to the x's at the end. So I worked in u's all the way, and then at the end subbed the x's back in. Last one, integral of f at u dx. Is this the same as either of these things? So integral of f at u is u cubed plus 1 dx, which I can't do. Ooh, what's going on here with my pen? Oh, we're moments away from this computer doing the funky chicken. I got to wrap this up and get this video saved before the computer explodes here. Can't do this integral as it is because it's u cubed plus 1 dx, but I can do this. Is go get u, which is x squared, go get u, that's funny, x squared cubed plus 1 dx. And so I get integral of x to the 6th plus 1 dx, which is something different again. What's the lesson? What is at the end here, this dx, du, dx matters. You know, whereas other times it seemed like it didn't matter what variable we were using. But in the integral it matters. And it feels like I'm changing rules. I'm like, no, new situation, new rules. Yeah? And again, I'm not setting you up for something here. I'm not. I just want to draw your attention to it so that when you see those things, you know what's happening. Questions? There. Okay, that'll be the end of this part of the video. I'm not speaking to you guys in my class here, I'm speaking to video people. And we'll pick up the rest of the video at the bottom line there, substitution and indefinite integrals, almost like a separate topic within the lesson.